Okay, I think we'll get started. So today we're going to do an overview of the results of quantum mechanics for hydrogen, and we'll talk then a little bit about the quantum number rules as well. Okay, so getting into the results, and again, we are not going to be going through the solution here in this course. We'll have to wait till later in the curriculum, but we certainly want to look at some of the results. And so by results, I'm referring to how quantum mechanics describes the behavior of the electron. So the first thing is that the electron's position about the nucleus is described by something called a probability amplitude. Now there's a lot of subtlety here. This is not quite a probability distribution, like a distribution of test scores, for example, but it is close to one. What one would have to do is take what's called the modulus square, or you can just think of it right now as squaring this value so that you square the probability amplitude to get a probability distribution. These probability amplitudes are generically called wave functions, and when they apply to hydrogen, they are referred to as atomic orbitals. So if you are looking in your general chemistry book, you may not even see the word wave function, or it would be mentioned very briefly. And quickly, these functions of space around the nucleus that describe where we will find the electron. What's the probability of finding the electron? If we take the atomic orbitals and square them, we get that information. We get that probability distribution. That's what it means to solve the quantum mechanics for hydrogen. We get these orbitals, and it's stuff that people can do, and we will look at those solutions again later in the curriculum on how to get them. The electron in hydrogen actually lives in 5 dimension. Our three spatial dimensions, x, y, z coordinates, and then a separate spin space. Now, although the space is separate, there is a physical interaction with the 3D space. In particular, the intrinsic spin character, so the nature of spin in the spin space, will interact with a magnetic field in our 3D space. Now, one of the rules of, or one of the sort of theorems of quantum mechanics is that you get a dimension, or for every dimension that you quantize. So by quantizing, it means we're somehow constraining it in some way. So in this case, the nucleus is positively charged, so it's collecting the electron around it. Whenever you quantize a dimension, you get a quantum number. So we expect hydrogen to be described by 5 quantum numbers. And then finally, there is a principal quantum number that determines the limits of the other quantum numbers. And very interestingly, the energy of hydrogen in one of its atomic orbitals is determined only by its principal quantum number. And in fact, this is really interesting. The formula is exactly the same as what was for the Bohr model. Now, we will see that where the Bohr model broke down, like putting well, we won't see this, but I'll say this. When the Bohr model broke down, like in a magnetic field or an electric field, that won't happen here for hydrogen because we've done the calculation. But you can see how the Bohr model actually did a pretty good job of getting that, and that's why it agreed experimentally with the both the line spectra and the energy, ionization energy. Okay, well, that's an overview. So let's look at the quantum number rules here now. The primary quantum number, the principal quantum number, is labeled n. So the n quantum number is the principal quantum number. This is referred to as sometimes called the energy quantum number, or the physical property it's associated with is energy. Sometimes also called the shell. the shell. And we'll come back to that a little bit later when we talk about elements with more than one electron. The rules, okay, so these are the rules, and these just come out of the math of quantum mechanics, is that the value that n is allowed to be is 1, 2, 3, etc. Okay? So n could take on any of the counting numbers, 1 up to infinity. The next quantum number, there's kind of a hierarchy here for the spatial quantum numbers, and that is L, so the angular momentum. And it represents the total angular momentum of the electron in a particular wave function or atomic orbital. These are sometimes referred to as a subshell. Subshell, and again, that'll make more sense when we talk about multi-electron atoms in the periodic table. L takes on values 0, 1, 2, 3, up to n minus 1. So that's the important thing here. N acts as a constraint to how high L can be. And one thing I want to carefully stress, and I'll keep doing that, is this is a limit. It doesn't mean that L is n minus 1. It can mean any number up to n minus 1. So if n is 3, for example, then n minus 1 is 2. So L could be 0, 1, or 2, but not 3, for example. All right, the next quantum number, which is actually dependent on L now, so there's this sort of this hierarchy, as I mentioned, is the angular momentum orientation quantum number, or M. And this physically represents the orientation in space of the angular momentum. Now, there is more to it than that, and when in our next video, when we talk about the atomic orbitals themselves, we'll go a little more into the subtleties of the quantum number M. The rules here are M is 0, plus or minus. So M can be a negative number, plus or minus 1, plus or minus 2, up to plus or minus L. And so let's look at this hierarchy again. If n is 3, right, then L could take on any of these values. If L took on, say, 2, then M could take on any of these values, up to plus or minus L. All right, now we leave the 3 spatial dimensions. We've got our 3 quantum numbers for the spatial dimensions that we've quantized. So these are called the spatial quantum numbers. The spin quantum numbers, then, are spin itself, S, and this is really quite unfortunate, actually, because of this idea that you should get a quantum number for every dimension you quantize. You have to have 5 quantum numbers. But in many general chemistry books, and you might want to check yours and see how they do it, they'll just say there's 4 quantum numbers, and they don't include S. Now, the reason for that is that S is and always is 1/2 plus 1/2 for an electron. And in general chemistry, we don't talk about quantum mechanics of anything other than the electron. So that's why some authors in the general chemistry textbook often don't include it. So if you check your book, whatever book you're using, and you read that there are 4 quantum numbers, there's actually 5, and you'll notice that S is missing. Okay. A number that certainly won't be missing in every Gen Chem book is going to be the spin orientation quantum number, M sub S. And M is chosen for a reason. It's analogous to this M. And it takes on values of minus 1/2 or 1/2. And we give those names as chemists. We say if it's a minus 1/2, we call that a spin down. And sometimes we use a down arrow. Sometimes we'll use the Greek letter beta for a spin down. And then if it's a plus 1/2, we refer to that as a spin up. And we give it an up arrow. It's a little misleading because up and down sort of make us think about our 3D-dimensional space. Remember, this is happening in the spin space. Where the words up and down come from is, as I mentioned, spin will interact with a magnetic field that's present in our 3D space, and up means aligned with the field and down means aligned anti to the field. Let me just, before I end here, let me just say, come back to L real quickly. And while L takes on these numerical values in the math, we often substitute with letters. And so if L is 0, we call that an S subshell. If L is 1, we call it a P subshell. L is 2, we call it a D. There is no E. I think mainly because charge of an electron is E, and then the natural number E, there's too many E's. So it's F, G, H, and so on up the alphabet. The reason it's not ABC, I think, is historical, coming out of atomic spectroscopy. S, I think, refers to as sharp, P as principal, and D as diffuse, as kind of descriptive words for the spectra of hydrogen. Okay, so this is an overview. So again, in summary, there are 3 things we look at: the wave function, or from now on we'll call it the atomic orbitals, the quantum numbers, and you want to start getting these rules down. So just practice them. Try to write them on a blank sheet of paper, set it aside for an hour, 2 hours, try to write it again until it's completely internalized. You really do want to memorize these rules, because there's no way to go back and derive them until we've gotten a lot further into the curriculum. Okay, and then finally, the energy levels. So over the course of the next few lectures, we're going to spend a couple of lectures on the atomic orbitals and 1 lecture on the energy levels. So we'll do the energy levels next, and then we'll do 2 of the two videos on the atomic orbitals. Now, I would suggest perhaps sort of watching this whole collection, this video, and then the other 3 videos dealing with the orbitals and the energy levels all at once. So watch them all at once, then start working the homework together collectively, because you can't really think about these independently like we are doing with each of the videos. You have to kind of view that as a collective. So go through, watch these next few videos, try to internalize, keep telling yourself the story of it, memorize the quantum number rules. We'll have a couple of other things to sort of memorize, although I'll give you some strategies for not having to completely memorize them.